right, here's our notes for transformations of parent functions. What we have at the top of the page is a generic form for the different ways you can alter an original equation. And then down here, we will explain what happens when that alteration occurs. So this is function notation for just a generic function g of x. And this x in here. So imagine our parent function is the linear or identity function, g of x equals x. The four different ways you can alter this x is you can add or subtract something directly to it. You can multiply it by something. Then out in front of that entire function, okay, so let me back up. This b is being multiplied by the x. This a is being multiplied by the entire function. And then this k is being added to the entire function. So if you are, so just starting at the inside here, if I'm adding or subtracting something directly to the x, this is going to be a horizontal shift. It will move your original graph left or right. And if you have done math at Johnson, we always say this is an insider's lie situation. If it's inside the parentheses, the brackets, the square root, whatever, if it's inside and it's being added or subtracted to the x, you're going to do the opposite. So we're going to add the opposite of h to the x values. So if we have a minus h, so if it was a minus 3, we're going to add 3 to the x values of the original function. So if you have a negative h, that means you're going to shift to the right. And if you have a positive h, you're going to shift the graph to the left. Now, if you have a constant in front of the x, but not in front of the entire function, and what I mean by that is, let's say our function was g of x equals x squared, and I had a constant of 2. This is in the b position. This is inside and being squared. If the 2 was here, it is separate from the x squared, and we would consider that out front. So this 2 is what I mean by out front of the function. This 2 is what I mean by inside of the function. So if you have a constant that's inside with your x, this is going to be a horizontal stretch or compress. Stretching mean your x values would expand out to the left and right from their original position. Compress meaning the x values would shrink in from their original position. And in this case, it's still an insider's lie situation. But instead of adding the opposite of what you see, you're going to be multiplying by the opposite of what you see. So you will multiply x values by 1 over b. You are multiplying by the multiplicative inverse. And then if you have a constant in front of the function, like this 2 here, versus this 2 which was inside, we're talking about this 2 which is outside, right? It's 2 times the x squared. This is going to be a vertical stretch or compress. Because what's happening now is you're taking your original y values, whatever your original output was, and you're multiplying it by 2. And you can see that here. Imagine you put 1 in for this x in the original function. You put in 1, 1 squared gives you 1 back. So your x is 1, your output is 1, your y is 1. But in this case, once we multiply it by 2, we're plugging in 1 for the x still, so the x value stays the same. Following our order of operations, we would do 1 squared is 1, then times the 2, which would make my y value 2. So when your constant is out front, your x values will stay the same, your y values will be multiplied by whatever that a value is. So what we're going to write here is multiply y values by a. So you can see that if your a is bigger than 1, it's going to stretch your graph. If your a is less than 1, meaning between 0 and 1, it's a fraction, it will compress your graph. And then the k on the end is our vertical shift. This means the graph is going to be going up or down. The horizontal shift was going left to right. So it's on the very outside of the function. So you've plugged something in, you've simplified everything that was being added, subtracted, multiplied to the x. According to order of operations, this is the very last thing that's going to happen. So you're going to take those y values, your outputs, and add or subtract whatever that k is. Add or subtract k to the y values, your original y values. So if you see a plus k, your graph is going up. If you see a minus k, your graph is shifting down. All right, and what we're going to do is practice single transformations, and then we have some problems where there will be multiple transformations. So what I'm going to do is just do one problem from each of these single transformation sections. I'll do the one on the left, and then you can practice the one on the right and check yourself with the answer key that's in your Google Classroom. But I'm not going to put the second ones in the video, just the first ones on the left. So here we have x squared minus 3. So you can tell because of the square that my parent function was x squared. And what I'm going to do is fill in my domain and range. That were the parent points that we did on that yellow sheet the other day. So I'm going to put -2, -1, 0, 1, 2, and my y values were 4, 1, 0, 1, 4, because that's what we get after we plug it into x squared and square it. All right, so this -3 is outside or at the end of the equation. So that means it is a vertical shift, and it is going to go down 3. So that means I take my original y values, and I'm just going to subtract 3 to each of them. So my x's stayed the same, and my y's are now 1, -2, -3, -2, 1. Now I'm going to show you the parent function before any transformations happen. Now I did the table here, even though it's just one single transformation, and we could do it just intuitively. If the graph is shifting down 3, I can just take each of my parent points and push them down 3 places. Or do your counting pattern from the original one. All right, so I just pushed it down 3, but let's verify that it matches the coordinates of the new points that we did in the table. So you see here I have a point at -2, 1. -2, 1 is right there. My next one is -1, -2. -1, -2, right there. 0, -3 is my next point, right there on my graph. 1, -2, and then 2, 1. Right? So my intention is for you to pause the video and do this problem by yourself, check it with the key in your Google Classroom, but I won't be including this one in the video. And real quickly, I want to say what it would have looked like if I had had a -3 that was inside the function. Then that would have been a horizontal shift. So here's a different problem, just so you can see the difference. Right? The original function is still an x squared, but now there's a -3 inside with the x. this minus 3 is outside the function of x squared. So this would be a horizontal shift to the right 3. This is a vertical shift down 3. Okay, so let's look at horizontal shift now. So on the left, we have absolute value of x minus 4. So you see the absolute value bars. That is how you know that the parent function is absolute value of x. So I'm going to write in my parent values that we did on our yellow reference sheet. And I'm going to come out to the left a little bit because I know I'm about to change my x's. Minus 4 is a horizontal shift. You're going to be adding 4 to all of your original x values. So I'm going to write these over here, -2, -1, 0, 1, 2. My y values were all positive. Here's the parent function. And if I have a minus 4 inside with the x, I'm going to be doing the opposite, which means add 4 to all the x's. So +4, +4, +4, +4 all the way down. So I will shift the graph to the right 4 places. And I'm going to just do the counting pattern here real quickly. And then verify with our table. So I should have a point at 2, 2. Absolutely. Point at 3, 1. Right there. A point at 4, 0. A point at 5, 1. And a point at 6, 2. So I'd like you to pause your video and try this problem. Figure out your parent function, write down the parent points. You don't have to draw the parent graph. I just like to for reference. So pause the video, try that one, check it with the key in your Google Classroom, and then come back to the video. All right, so now we're talking about vertical stretch or compress. In this problem, we have 3 times the square root of x. So my original parent function that has been modified is the square root of x. So the parent points that we used for that, the domain was 0, 1, 4, and 9, because those are perfect squares, so it's easy to take the square root of them. And square rooting them gives us 0, 1, 2, 3. And when we are multiplying by 3 on the outside of the function, that is going to change my y values. So I take the original y's and multiply all of them by 3. So I have 0, 3, 6, 9. Here's my parent graph. Somewhere out here. So now my new points, I have one at 0, 0. Okay, so this is not a shift left and right or up and down. So the 0, 0, that's why it stayed the same. So then my next point is 1, 3. My next point at 4, the y value is now, instead of at 2, it's at 6. And then all the way over here at 9, it's up here somewhere. Right. So you can see that when there's a number in front and you're multiplying all your y's by that number, it's going to stretch the graph up. If this number right here was a fraction, 1/2, 1/3, it would take your y's and make them smaller, and so they would compress to, that would compress your graph to below the original one. So you take a minute and pause the video, do the second graph, check it with your Google Classroom key.